Very onset, would like to thank the organizers for giving me this opportunity to teach in this wonderful school. I have taught earlier also, but that was on relativistic kinematics. This is the first time I am teaching this experimental overview or relativistic of heavy-ion collisions. So I will try to go rather slowly because since this is a virtual lecture, and the participants are I will be very happy if you can, whenever you feel like, you can stop me if you have some questions. Okay, so let's start with the introduction. Even though many of those things have already been discussed by Sandeep, but still for the completeness we will discuss them. So our aim is to study the physics of ultrarelativistic heavy-ion collision experiments. And as you know that this is an interdisciplinary field. This is the high energy physics of elementary particles as well as the nuclear physics. As you all know, nucleus is a many-body quantum system. And by heavy ion, generally, what we mean is by heavy atomic nuclei like lead or gold. Like in AGS or in RIC, in Brookhaven National Laboratory in USA, we always have gold-gold collisions, whereas at CERN we have lead-lead collisions. So these are the heavy atomic nuclei. But whether in low energy nuclear physics, in the low energy nuclear physics, the heavy indicates anything beyond alpha particle. That is Z greater than 2. And by ultrarelativistic, what we mean that the kinetic energy is much greater than the response energy of the particle. So the higher the particle physics deals with single particles like leptons, quarks, and hadrons, and they are basically what you want to do is to derive the underlying interaction or the spectroscopy. The different quantum numbers of these high energy particles, their energy states, their masses, and so on and so forth. Whereas nuclear physics deals with the extended complicated objects like nuclear, where interaction is described by effective models like your Snell model or your mean field theory, things like that. So in alternativistic heavy-ion collisions, one tries to analyze the properties of this hot and dense produced matter in terms of the elementary interactions. This basically is driven by the search or experimental search to theoretically predict the new phases of nuclear matter and the identification of the phase transition between the different phases of nuclear matter and a possible reconstruction of the QCD phase diagram in terms of thermodynamic parameters like temperature and baryon-chemical potential. So what is the big idea? The big idea is like this: the quantum chromodynamics of QCD is the theory of strong interaction, and in the QCD exhibits a rich phase structure. Alternativistic heavy-ion collisions gives us the opportunity to create the QCD matter at extreme temperature and densities in the laboratory. And once you vary the collision energy or the colliding species, you can create the hot and dense nuclear matter over a wide range of temperature and density. And this basically gives you access to the different phases of nuclear matter, because depending on the collision energy, when two nuclei collide, either you might create a hot hadronic matter, which people talk about this hadron resonance gas or HHG, or the partonic matter or the Quark-Gluon matter. So the ultimate experimental aim is a quantitative mapping of the QCD phase diagram in the T-mu plane in laboratory. So this is the conjectured QCD phase diagram. Just now in Sandeep's lectures, he beautifully discussed the different features of the QCD phase diagram, and I will do it in a very brief and rather in a qualitative manner. So the thermodynamic properties for any macroscopic matter most readily expressed by a graph called phase diagram. So this is the graphical representation of the different phases occupying different regions of plot, whose axes are calibrated in terms of some external or control parameters. Each point in the diagram corresponds to a stable thermodynamic phase. Up till now, what I have told is true for the phase diagram of any macroscopic matter or any thermodynamic phase diagram, for example, phase diagram of water. So the nuclear matter, you all know, is governed by the strong interaction. So, and this nuclear matter is also believed to have a rich phase structure, and it is often expressed in terms of T and mu, the temperature and the baryon chemical potential. So I had a question for you. I set up a question that why QCD phase diagram is often plotted in terms of T and mu, but it seems you already had the answer in the previous class. Okay. So in the low temperature or baryon chemical potential, you have the confined phase. These are the hadronic phase or hadron resonance gas phase. Here the degrees of freedom are small, whereas in the high temperature or high baryon chemical potential, you have a deconfined phase made up of quarks and gluons, and here you have a large degrees of freedom. Why you have a small degrees of freedom and why you have a large degrees of freedom in the QGP phase and small degrees of freedom in the hadronic phase? Because hadrons are color confined objects. As soon as this transition from hadron to QGP takes place, you have a liberation of the color degrees of freedom. And this makes the effective degrees of freedom very large in the QGP phase compared to the number of degrees of freedom in the hadronic phase. And this basically, and you will eventually see, probably you will see in your theory course that the thermodynamic quantities like energy, pressure for a baryonless system, you can write it as T to the power 4, temperature to the power 4 times the effective number of degrees of freedom. So more will be the number of degrees of freedom, more will be the energy density, more will be the pressure. And here you have an abrupt release, certain release of degrees of freedom as the transition from hadron to QGP, hadron to QGP transition takes place. However, when we talk about hadron to QGP transition, there are two underlying transitions. One is the deconfined transition, because your quarks and gluons are confined inside your hadronic phase, which undergoes deconfinement, and they are deconfined in the QGP phase, the partonic phase. So this is called a deconfinement transition. And another transition is known as the chiral transition. So in the hadronic world, your chiral symmetry, which is a fundamental symmetry of QCD, is spontaneously broken. And as soon as the matter makes a transition from hadronic phase to a partonic phase, this spontaneously broken chiral symmetry is restored. You know that whenever there is a change of phase, there is an abrupt change of the symmetry structure of the system. Okay. So that for the deconfinement phase transition, the underlying symmetry is known as the Z3 symmetry or center symmetry. Sometimes this is like an up and down Ising symmetry. And this is an exact symmetry in the limit of MQ quark mass tending to infinity. There is another symmetry which is called the chiral symmetry, or chirality means handedness. The chiral symmetry, which is an exact symmetry in the limit of quark mass tending to 0. So in physical world, you know the quarks have the finite masses. So none of the symmetries are exact. Okay. So they both of the symmetries are approximate. Okay. So this is the phase diagram. We are conjectured QCD phase diagram as a function of temperature and baryon chemical potential. So at very high temperature and small density, small mu, and densities, instead of densities, we just write the baryon chemical potential. You know, this baryon chemical potential is basically related to net baryon density, which is or net baryon number, which is conserved in heavy ion condition. Okay. So what do we know about the deconfinement transition and chiral transition? I will just discuss them very on a qualitative level, because Sandeep is having real quantitative discussions on this. So the degrees of freedom changes from color for deconfinement transition. Degrees of freedom changes from color neutral hadrons to colored parton, the quarks and gluons. So this is equivalent to the insulator conductor transition in QED, or in your condensed matter physics, which is known as a Mott transition, that you have from a dielectric to a conductor. Okay. So each for a real phase transition, there is always an order parameter. What is an order parameter? Order parameter is something which basically defines a phase. In one phase, order parameter has a 0 value, which is the disordered phase, and in the or more symmetric phase, and in the ordered phase, your order parameter has some non-zero value, and if you properly normalize it, it will become unity. Generally, phase transitions are classified with respect to the order parameters. For a first order phase transition, your order parameter has a discontinuous variation along the transition, and for a second order phase transition, your order parameter shows generally a continuous variation. So what are the order parameter here for this confinement to deconfinement phase transition? This is something called expectation value of Polyakov loop, which is a complicated QCD quantity which we don't want to discuss. But for us to have a physical meaning, it is basically, you can write it as e to the power minus f by t, where f is the free energy of a q cube pair. free energy of a quark antiquark pair. Okay. So in the confined phase, you know this free energy will be very large because of the confinement property of QCD. You cannot isolate a quark from an antiquark, or you cannot separate or you cannot isolate two quarks. So your free energy of the system of your in the confined phase, free energy will be very large. If free energy will be very large, then your expectation, because L goes as e to the power minus f by t, so L will tend to 0, or expectation value of the Polyakov loop would be 0. Whereas in the deconfined phase, you always find your free energy will be small. Why? Because in the deconfined phase, you always find in the immediate vicinity of a quark another quark or antiquark, which means your free energy of a QQ bar or a QQ system will not be very large. This will be small, and hence your expectation value L will be non-zero. Also, when you have, that means in terms of this deconfinement transition, your confined phase is a disordered phase, whether your deconfined phase is an ordered phase, okay? Or your center symmetry is broken. Your center, this is why your center symmetry is broken in the confined phase. Sorry. The center symmetry is broken in the confined.
Hello, Partha. We can't hear you. Are you still there? Hello. Can anyone hear Partha? Is my problem or? No, sir.
No, sir, we cannot hear Partha.
Let me call.
Okay, so I was discussing about the deconfinement transition, and another transition that takes place is the chiral transition. Chiral symmetry, as I say, is a fundamental symmetry of QCD, which is spontaneously broken in the hadronic world. And once the system makes a transition from hadron to QGP, this spontaneously broken chiral symmetry is restored. So here the order parameter, as Shundil has already discussed very nicely, is chiral condensate. And one looks at the temperature dependence of this chiral condensate, which is non-zero in the confined phase or in the hadronic phase, and 0 in the chiral symmetry restored phase. Okay. So what we know as of now, as at small mu b, in the region of small baryon chemical potential, in the small mu b in the region of small baryon chemical potential, the lattice QCD predicts a smooth but rapid crossover between hadronic phase and QGP phase. So the crossover has been discussed many times, but there is no harm in listening it, discussing it once more. This crossover transition is not a true phase transition, because we know the true phase transitions are characterized by the discontinuity or singularities in the thermodynamic variable. You take derivatives of the, for the thermodynamic system, you calculate the free energy, and then you take derivative of this free energy with respect to temperature. So the first derivative of free energy with respect to temperature generally gives you specific heat, and the second derivative generally gives you first derivative gives you entropy, and the second derivative generally gives you if you take the derivative of free energy with respect to temperature, that gives you specific heat. Similarly, if you take a derivative of the second order derivative of free energy with respect to other quantities, they give you susceptibility. So in a first order transition, your first derivative of free energy is discontinuous. For example, the first order derivative of free energy with respect to temperature gives you entropy. So a first order phase transition generally characterized by the discontinuous entropy. And you know from your basic thermodynamics that T into S, T delta A, if delta S is the amount of the entropy difference between the two phases for a system undergoing first order phase transition, then this T delta S, this has a dimension of Q, delta Q, temperature, heat, and this is T delta is called the latent heat. So first order phase transitions are often characterized by non-zero latent heat. On the other hand, for a second order phase transition, your latent heat is zero because your first derivative of free energy is continuous. Here, your second derivative is discontinuous. Okay, but for a crossover transition, if you go up to the nth other derivative of the free energy, all of them will be continuous. They will not be discontinuous. So you do not see any discontinuity in any of the thermodynamic variables, whether it is a first order derivative or a second order derivative of your free energy. So the lattice QCD predicts a smooth but rapid crossover between the hadronic phase and the QGP phase. But then how do you know that there is a change of phases has occurred? Because if you look if you plot this temperature dependence of the order parameter like average value of Polyakov loop or the chiral susceptibility, there you see there is a sharp variation or a sharp change even though there is no discontinuity. And then the peak and width of this the chiral susceptibility, which is the second derivative of the free energy or the partition function of the system with respect to the quark masses of up and down quark. So that this chiral susceptibility shows a pronounced peak as a function of temperature. The peak position and the width are independent of the volume. This basically tells you an analytic crossover transition, which is not, again, I'm telling, it is not a true phase transition. An example of analytic crossover transition is, for example, the ionization. That you take a hydrogen gas and you start heating it, eventually it will become an ionized plasma of H plus, hydrogen plus, and electron, that is proton and electron. This transition is a smooth transition as a function of temperature, and this is not as a crossover transition. The transition temperature, as we know that from the latest lattice QCD results, is of the order of 155 MeV. And the chiral and deconfinement phase transitions occur nearly at same temperature. At large VUB, at large baryon chemical potential, that is in this region, in the large baryon chemical potential, we know that the lattice QCD doesn't work because of the sign problem, which Shwati has already discussed yesterday. So the lattice QCD results are not directly applicable. However, there are different theoretical model calculations. There are certain effective models or phenomenological models which basically work in this large VUB regime, and these models suggest that there is a first order phase transition between hadronic phase and the partonic phase. In case of a first order phase transition, you have a definite phase boundary that the two phases are can be completely separable. Okay, so the theoretical model suggests a first order phase transition between the hadronic phase and the first order and the partonic or the Quark-Gluon plasma phase. And the first order phase transition line, which is shown here, the first order phase transition line basically ends at a point which is known as the critical end point. And at this critical point, the transition is second order. And as per present lattice QCD results, the critical endpoint is unfavored for mu by t less than 2.5. So this says it is between 2 to 3. Between the mu b by t ratio between 2 to 3, the transition is still crossover. There is no signature of the critical point, which basically means not only at mu b equal to 0, up to some certain values of mu b, the crossover transition occurs. So this is shown by this dotted line, which you can call as a crossover line. Okay. So there are a few questions here which I just noted down, and I will circulate one assignment for you where all these questions are there. You are requested to work them out. They are very simple ones. The first question is, why is QCD phase diagram often plotted in terms of T and UV, temperature and baryon chemical potential? Also, if you look at in this axis, T equal to 0 line, that is the mu B axis, you will see here what sits is the normal nuclear matter or the nucleus. And the mu B for the normal nuclear matter is 1000 MeV or 1 G. So the question is why normal nuclear matter has a UV of 1 GeV. And the third question, as we said, when there is a hadron to QGP phase transition, there is a liberation, there is the degree, effective number of degrees of freedom suddenly increases by a large amount. So what we have, just to convince yourself, I have just said that you count the number of degrees of freedom of a pion gas and a two flavor Quark-Gluon gas, two non-interacting Quark-Gluon gas. Two flavor means it will be made up of U and D quark. You will see the number of degrees of freedom for a Quark-Gluon system is much higher than the number of degrees of freedom in a pion gas. So let's proceed. So let's just start begin from the beginning. So we know there are the four fundamental interactions in nature, and that interaction which we will be dealing with the strong interaction, and the underlying force is the strong force. So these are the fundamental constituents of matter. This has already been discussed when the time is started. So we know that the basic ingredients of the visible matter, that is the nucleus, the basic ingredients of the nuclear matter are the up and down quarks. Apart from that, there are basically three families of leptons and three families of quarks. Up and down, charm and strange, and top and bottom are the three families of quarks. And then there are three families of leptons: the electron and the electron neutrino, the tau and the muon and the muon neutrino, and tau and the tau neutrino. And the visible matter are basically made up of up-down quarks, which make up the proton and neutron. A proton is up and down, and a neutron is up, down, and down. And then nucleus, and this is surrounded by the electrons. Okay. And then the strong force is mediated by exchange of a massless particle known as massless chargeless particle known as the gluons. So the strong interaction that is basically described by the strong QCD QCD coupling constant or QCD running coupling. Okay. So the coupling constant for any interaction measures the strength of the interaction. So the QCD coupling constant is sometimes called the running coupling constant. It decreases, as you can see from the figure, as you already know, that it decreases logarithmically as Q square increases or R decreases. What is Q square? Q square is the square of the force momentum transfer between two particles which interact among themselves via strong interaction. And you know from the uncertainty principle that the momenta and R are inversely related to each other. So you can, if a momentum transfer in a certain process is Q, the physical separation between them is the order of h bar by q. Okay, this is just from the uncertainty principle. So the higher Q square means smaller r. So smaller be the separation between higher be the momentum transfer in a strong interaction process, but smaller be the separation between the particles which interact strongly. Smaller and smaller will be the value of alpha s. The high Q square means small alpha s. Your alpha has become extremely small. So that the strongly interacting particles will behave nearly freely. This is what is known as the asymptotic freedom. And because of small alpha s, one can make calculations by expanding the Hamiltonian in terms of the series of alpha s. This is known as the Partha. This technique is known as the perturbative QCD or perturbation theory in strong interaction or perturbative QCD. So many high energy physics processes can be successfully described using this perturbative QCD process. However, at large distance, a small q which is comparable to the size of a nucleon. So by large distance or small q, I mean q of the order of 1 GeV, or this physical separation is of the order of 1 Fermi, which is the radius of a proton, which is nearly the radius of a proton. So when compared at a momentum scale of small q of the order of 1 GeV or at the length scale of the order of 1 Fermi, the interaction between two quarks is strong. So this amplification of the strong force with decreasing q, alpha is increases. The amplification of the strong force with decreasing q or increasing r is known as infrared slavery. As a result, we say that QCD vacuum is an anti-screening medium. For a QED, for the your electromagnetic interaction or Coulomb interaction, which is of the type of alpha by r, 1 by r, alpha electromagnetic by r, as the distance increases, the strength of the interaction decreases. It becomes more and more weakly, the strength of the interaction becomes weaker and weaker. On the other hand, for QCD, as the distance increases, the strength of the interaction increases. This is the property which is known as the QCD vacuum basically behaves as an anti-screening medium that you go away and away from a tester, you feel stronger and stronger force. And one of the outcomes of this infrared slavery or this anti-screening is the confinement. That means you cannot observe free quarks in the laboratory, or quarks are always confined inside the hadrons in the normal world. In the normal world, quarks are always confined inside the hadron. You know that at small q, since the momentum transfer for such processes is small at the length scale of the order of the size of the hadron, the q is the momentum transfer is small. You cannot apply PQCD. The perturbative QCD techniques are inapplicable. So this is basically the non-perturbative domain, and there are no first principle analytical calculations are available to do that. However, the phase transitions in strongly interacting matter, which we are going to talk about, they basically occur in non-perturbative domain of QCD. So what to do then? How do you study this non-perturbative? How do we study the non-perturbative interactions, QCD interactions, or non-perturbative effects? In the theory, either you have to do some model calculations, or you have to take help of the numerical techniques like lattice. And this is why this relativistic heavy-ion collision is so important. Whereas in the experiment, your inputs about this phase transition in QCD comes from the relativistic heavy-ion collision experiment. That is why sometimes this relativistic heavy-ion collisions are sometimes is known as an experimental implementation. Because this lattice QCD also has its limitations. Because it cannot be applied to high movies. So are the phenomenological models which are not based on first principle calculation. And that is why this physics of relativistic heavy-ion collision is driven, many a times it is called an experimental field, but this is driven by the experimental data. So let's start with a little bit of history. How did it start, or how did this field all began? So way back in 1951, Pomeranchuk basically he gave an idea that the hadrons have an intrinsic size. The radius of a hadron is of the order of 1 Faraday. So because of this intrinsic, they have some finite size. They occupy a finite volume in the space. So if you consider the hadrons to be a sphere, so its volume will be 4 pi r cube. So this basically gives a limiting density of the hadrons, that which is inverse of the size of a hadron. This gives you NC of the order of 0.24 per Fermi cube for the hadronic matter. That means this is if you increase the density beyond this point, these hadrons will start overlap with each other. Okay, because of their finite size, you increase the density beyond these points, the hadrons will start overlap with each other more and more, and eventually they will lose their identity. Then in 1965, Hagedorn first addressed the question of the fate of strongly interacting matter at very high temperature. What happens to the QCD matter or strongly interacting matter at extremely high temperature? Remember, this is a time when QCD is still not yet mature or still not yet formulated. So this is the pre-QCD era. He came up with a statistical bootstrap model, and according to he gave the mass spectrum of hadrons is basically goes as m to the power minus 5 by 2, and mh is the mass of the hadron into e to the power mh by th. Here th known as the Hagedorn limiting temperature, and which basically has a value between 160 to 180 MeV. And all thermodynamic quantities diverge for T greater than Th. Beyond this Hagedorn temperature, basically you cannot heat up a matter. So all energy supplied to a system beyond this Th is used for particle production. This will not increase the temperature of the particle. This is the limiting temperature, the maximum temperature to which a matter can be heated. And above which, if you still start supplying energy to the system, all energy will be used for particle production. And we know this is possible because you have enough energy. We know from Einstein's mass energy relationship, you can create particles. So in early and middle 70s, the QCD theory was formulated, and we know by that time we knew that the hadrons are not elementary objects; they have a substructure. They made of more fundamental particles, quarks and gluons, and pre-quarks as well as gluons. They carry something. They have a quantum number called color. The pre-quarks and gluons carry color, and since they carry color, they cannot be directly observed in the laboratory experiment because all hadrons are colorless objects. In 1975, Kabibu and Parisi, they basically talked about the Quark-Gluon substructure of hadrons, which opened up the possibility of a phase transition. Because of this Quark-Gluon substructure of the hadrons, they talked about the possibility of a phase transition to a new state of the confined quarks and gluons. This is a new state of strongly interacting matter, where the basic ingredients or the basic degrees of freedom are the confined quarks and gluons. So the limiting temperature of the hadron is immediately identified with the phase transition temperature between the colorless finite size hadrons to the colorful point-like quarks and gluons. And they are the people who first give a sketch of the QCD phase diagram of nuclear matter. Then, in along the same time, there were arguments from Collins and Perry, who said that such asymptotically free QCD also realized for large densities. So Kabibu and Parisi talked about large temperature. On the other hand, Collins and Perry talked about for large densities. And they talked about super dense nuclear matter, the nuclear matter where the density net baryon density exceeds much more than the many times the normal nuclear matter density, and where also the quarks will behave like asymptotically free, and instead of a hadronic matter where hadrons will dissolve, the hadronic boundaries will dissolve, hadrons will lose their identity. Instead, we have a dense multi-quark environment. But the question which was lingering around is how to produce such exotic states of matter, strongly interacting matter in the laboratory. And the idea came from a paper by T.D. Lee and G.C. Wick already in 1974, that higher the heavier collisions are the tool in which one can possibly create the novel abnormal states of dense nuclear matter by distributing high energy or high nucleonic density over a large volume that could restore the broken symmetries of physical vacuum temporarily. That means they can, by distributing a large amount of high energy or high nucleonic value over a high nucleonic density over a large value, one can create a Quark-Gluon phase of matter where chiral symmetry, broken chiral symmetry in the physical world is restored. So Edward Shuryak, in his one of the physics reports in 1978, first used the term Quark-Gluon plasma, along with the initial ideas of the space-time picture of the hadronic collisions, and the name was given due to the analogy with a similar phenomenon in atomic physics. In atomic physics, we have the QED plasma. Similarly, the matter which is produced in the relativistic heavier collision is seen to have expected to have similar properties, and that is why this is given a name of a plasma. So, but since the basic degrees of freedom are here not the ions and electrons but quarks and gluons, that is why it is called as a Quark-Gluon plasma. So what are the basic properties of a plasma? When we suppose we have a system of particles, when do we call it a plasma? When we call a system of particles as a plasma, it needs to satisfy some basic characteristics. So can anybody tell what are the characteristics for a system of particles to be called as a plasma? Hello?
It should be in ionic state.
Who is that? Can you please tell me your name?
My name is Prabhupada Dixit.
Okay, Prabhupada, you tell what are the conditions for a system to be called as a plasma?
There should be an ionic state and there should be collectivity.
Very good. And one more important feature should be there, which is collectivity is one very important feature. You are right. There is another important feature of any plasma. What is that?
Equilibrium, maybe. Yeah.
Equilibrium is, of course, equilibrium has to be there, but there are non-equilibrium plasmas as well.
Sir, quasi-neutral state.
Yeah, quasi-neutral state is one, but still one more. Anybody? This is device screening, right? Hello?
Yeah,
So
that
have you heard of device screening?
Yes.
is related to mean free path.
It's not related to mean free path. It's basically related to the screening of an interaction. Suppose you have a plasma. In a plasma, you have many unbound charges, right? You have many free charges. Now, suppose So suppose you consider a plus charge, a plus electron, and a minus charge, an electron and a position. Okay, suppose a positronium. So what is the interaction between the positronium? What is the potential be like? It is minus E square by R. So that is the attractive interaction under which the positronium is bound. As soon as you dip, suppose you take a positronium state and you dip inside a plasma, inside a QED plasma, what will happen? Because E plus and E minus, they have finite separation, right? This positronium has some finite size. So as soon as you dip an E plus and E minus, this positronium state inside a plasma, what will happen? The E plus or the E minus cannot see each other fully, because in vacuum there is no other particle present in between them. So the potential is like e to the power minus E square by R. Whereas as soon as you put this positronium state inside a QED plasma, what will happen? The interaction between E plus and E minus will be between E plus and E minus will be screened by the presence of many other many other electric charges, which will be present between this E plus and E minus, because they are always moving at a given temperature. Okay. So the attractive potential between E plus and E minus of the positronium will no longer be like E square minus E square by R, which is the Coulombic potential. Instead, it will be minus E square by R into E to the power minus R by RT. Right? This will be an exponentially decaying potential. This is known as the UCO potential. This is called a UCO type interaction. And what is RT? RT is known as the device screening radius. That means and R equal to RD, when the separation between E plus and E minus becomes equal to RD, the characteristic device length of the system, your strength of the interaction goes down to 1 by E of its original value. As a result, what will happen if the interaction between E plus and E minus gets reduced? Then E plus and E minus may no longer continue as a bound state, may no longer live as a bound state, or it may get dissociated. So device screening basically leads to the dissociation of bound states. So this is a very important characteristic of any plasma. And for QGP, the Quark-Gluon plasma, also we see the device screening, but here instead of electrical device screening, what we see the device screening due to the color charges. And because of this device screening of the color charges, certain bound states are not formed. This is known as Quark-Gluon suppression. So we will eventually see that. We will in our course of lecture we will eventually see. This Quark-Gluon suppression is something which happens because of this device screening, and this is basically one of the very important signatures of formation of QGP in relativistic heavy ion condition. The observation of Gaussian suppression. Okay, so finally, what is the definition of QGP? So QGP is a locally thermally equilibrated state of matter in which quarks and gluons are deconfined from hadrons, so that the color degrees of freedom become manifest over the nuclear rather than the nuclear equilibrium. What does that mean? That means quarks and gluons are no longer confined inside hadrons, and they are relatively free to propagate over a nuclear rather than a hadronic column state. So what are the essential features of the QGP? The degrees of freedom should be quarks and gluons, and matter should be at a local thermal equilibrium. And once the matter attains the local thermal equilibrium, it will exhibit, or it will show the collective properties of the, it will show some collectivity behavior and collective properties of the dense medium. How can we study QGP? There are two ways in study QGP. For example, in nature, our microsecond-old baby universe, the universe is born, or very old universe is born through an explosion known as Big Bang. So the microsecond-old baby universe, basically there the matter existed in the QGP form, but however in that QGP the number of quarks and the number of antiquarks are nearly the same. As a result, the net baryon chemical potential for such a plasma was zero. So that is why this is a baryon-free hot QGP. Similarly, in the core of the neutron stars, there the densities are so large that the matter there cannot exist in the normal nuclear state or hadronic state, and that because of the very high densities, matter might be existing there as a Quark-Gluon plasma state. However, this is a cold plasma. The temperature is close to zero, so there are no antiquarks. There are only quarks, and hence The system has a very finite, very high net baryon density and very high baryon chemical potential. So these are the baryon-rich QGP. So these are the astrophysical or examples of astrophysics or cosmology, a natural example where we can study plasma. But how can we study this plasma in the laboratory? We can recreate QGP in the laboratory, and this is often called as the mini bang because you are creating in the laboratory through relativistic heavy ion collisions. So the system formed in relativistic heavy ion collision, the system which is formed after the collision is often called as a fireball, and it expands instantaneously. Why it expands? Because the pressure inside is much more than the pressure outside, because outside there is vacuum, and inside a very high energy density is dumped, and hence the temperature and the pressure of the fireball is very high. So it expands instantaneously and remains far from turning to be a homogeneous system, and so the global equilibrium, as a result, the global equilibrium cannot be reached. You cannot have global equilibrium in QGP. However, your lambda, your mean free path, is much smaller than the system size, which basically helps to achieve local thermodynamic equilibrium or LTP. And in QGP, basically, when you talk about the evolution of the universe, initially the system was in the Quark-Gluon plasma state. Then there is the hadronization occurs and nucleons are formed. The nucleons are bound under the nuclear force to form the nuclei. Then the nuclei get associated with the electrons to form the atoms, and then molecules, and ultimately the entire universe after 15 billion years. Whereas when we study the QGP in the laboratory, we just run the evolution tree backward in time. You start with two colliding nuclei. They initially collide. They basically, the two nuclei collide and dump a large amount of kinetic energy of the initial colliding nuclei in the center of the collision zone, which basically excite the vacuum. And from the energy, many quark-gluon quanta of strong interaction are created. Eventually, they will scatter among themselves. They scatter among themselves. They interact among themselves to produce a locally thermalized medium made up of quarks and gluons, which is called quark-gluon plasma, which eventually undergoes hadronization, then evolution in the hadronic phase, and then freeze out. So in heavy ion collision, the occurrence of the sequence of these events is just opposite to what might have happened in your Big Bang.
So, Partha,
Yes.
can you just go back to? So here in that x-axis in the upper figure, this time scale,
Right.
10 to the power minus 6 second. This is the lifetime of QGP in the after the Big Bang, or
the time scales what is showing here. You are right. So the time elapsed. This is not the lifetime of the QGP. This is the time elapsed. Okay.
okay, so QGP system is formed after 10 to the power minus 6 second.
Exactly. Thank you for asking this question. Yeah, because that's why you always tell that the microsecond whole baby universe is in the QGP state. So this is the time elapsed. To happen that your time epoch starts at t equal to 0 is the point where your Big Bang explosion occurs, and then you just look at the time elapsed. And that is why you see the formation of this nucleons and nuclei is of the order of 3 minutes.
Okay, so it is basically when we go from QGP to nucleon states, then it's quite big time, right, compared to the QGP in the laboratory.
Exactly. So that is another important difference which you point out.
Okay. Okay, thank you.
Okay. So how can we create QGP in the laboratory? So these are the two facilities. One is the RIC and one is the LHC, and I do not need to tell you, but you all know that in RIC, both of them are collider machines. In RIC, we collide gold nuclear. In RIC, gold collisions take place, whereas in LHC, lead collisions take place. The STAR experiment, in which some of you are already participating, is a part of this RIC collider, whereas the ALICE experiment, where many of us are participating, is a part of this Large Hadron Collider. So how do we study QGP? We can create the QGP in the laboratory by relativistic heavy ion collisions, but how to study the QGP in the laboratory? So extremely small lifetime of the QGP produced in the heavy ion collisions The lifetime of the system is of the order of 10-20, which is of the order of 10 to the power minus 23 seconds. So this is a transient state. So there is no direct detection possible of this transient system because there is no detector in the world which might be as fast as to detect this QGP at on a level of 10 to the power minus 23 seconds. So we have to depend on the indirect probes. And what are the indirect probes? The indirect probes are the particles, final state particles, which are coming out from the collision zone. We have to measure all the final state particles which are coming out from the collision zone. And based on this, based on that, we need to find out signatures for the possible QGP production in heavy ion collision. To measure the particles, of course, we need detectors. And since there are different types of particles which interact with the detector material differently, so there are different detection techniques depending on the nature of the particle. As a result, your ALICE or your STAR experiments are a multi-purpose detector system. There are detectors of different types to have to measure to make a complete measurement of many kinds of particles. Complete simultaneous measurements of many kinds of particles. So, what are the general requirements of a detector? So it should have a large geometrical acceptance. That means it should have a maximum coverage for the produced particles over particles are produced over the entire phase space over 4 pi. So the detector should have a maximum coverage to measure as many particles as possible, and to sometimes to determine the geometrical objectives, you need to make Monte Carlo simulation to evaluate the geometrical acceptance of the detector. So also the detector should have a high efficiency and good signal to noise or signal to background ratio. So high efficiency means you should detect as many particles as possible within the acceptance, because the particles within the acceptance are incident on your detector, and not necessarily that you reconstruct all of them, you detect all of those incident particles. This depends on the detector efficiency. And an ideal detector, we need a detector as having efficiency as high as possible, and it should have good signal to noise ratio. Okay, which basically needs dedicated techniques for noise or background suppression. Detector should be having a high resolution so that you can precisely determine the particle properties, for example, its position, its momentum, its time, etc. And then you should have a good particle identification technique. There are dedicated techniques for identification of hadrons. For hadrons, for example, you depending on which hadron it is. For unstable hadrons, sometimes you use a technique depending on its decay topology. That means if it decays into 2 leptons or 2 hadrons, a particular particle, and you measure the decay products, and from the energy momentum conservation, you can reconstruct the mass of the particle. Let me give you an example. For example, there is a particle called Jepsa. So this Jepsa is a bound state of a charm and anti-charm quark, a C and C bar quark. It is very unstable and it immediately decays. Its lifetime is of the order of 10 to the power minus 20 seconds. That means for all practical purposes, it decays at the point where your collision is happening, where your nucleus collision is happening. It decays into a mu plus and a mu minus, a muon and an anti-muon, or an electron and a positron. So in your detector, what you detect is not the Jepsa, but the mu plus and mu minus. You reconstruct the 4 momentum of the mu plus and mu minus, and then you apply energy momentum conservation to calculate the invariant mass of this mu plus and mu minus pairs. And if you look at the invariant mass distribution, at the point of Jepsa mass, you will see a peak. There will be some background, and then you will see a high peak. You see a very sharp peak at the point of the mass of the Jepsa, which tells the presence of the Jepsa particle or Jepsa measure in the collision. Similarly, the electrons, they can be detected using the techniques of transition radiation, or using detectors like ring imaging Cherenkov counter, where they form some Cherenkov rings. The photons generally are detected by some calorimeters. And for the muons, the muons are highly penetrating particles. So basically, for to detect muons, you use some absorbers. The job of the absorbers is to absorb all other particles, and you put some detectors after these absorbers. So the idea is that all other particles get absorbed in the absorbers, and muons being highly penetrating, they will be able to penetrate the hadron absorber and reach on your detector. So the particles which give hits which passes through the entire absorber and give hits on your detectors, which are placed after the absorber, are generally considered as muons. So this is the basically the Alice detector setup, and probably all of you know much better than what I know about the Alice detector setup with different detectors. The heart of the detector is the TPC, the time projection chamber, which can be used for momentum determination, for tracking, as well as for particle identification based on DGX. But there will be more details on this will be covered by the lectures by Sanjeev. So I just keep it. So what we measure in the detectors is the raw data. Okay. So basically we record electronic signals in the data taking. We record electronic signals and monitor the detector status. And then what are the other next steps in your analysis from raw data to go to your physics plot? You need a calibration where you convert the electronic signal to physical quantities, for example, energy or energy. Then you produce the data. For example, you reconstruct each collision, or each nucleus collision is called one event. So you basically reconstruct the collision vortex, the position where the collision happens, and the charged particles with their momentum, position, and charge. And finally, you do some analysis where basically you correct for the detector acceptance, efficiency, and resolution. And finally, you get the physics plot. So before going to more details about the signatures of heavy collision, let's discuss about how to create QGP in the laboratory. As we said that relativistic heavy collisions are the tool to create QGP in the laboratory. But what are the critical and QGP can be created at extremely high temperature or at extremely high density. So we will do some order of magnitude calculations to have an idea what is the critical temperature required to create a QGP, or what is the critical density required to create a QGP. So we will consider just two limiting cases. One is the net at vanishingly small net barrier number. That for a system where your mu be equal to 0, that means you have equal number of baryons and antibaryons, or quarks and antiquarks in your system. So what will be the critical temperature for such a system? So suppose you consider an ideal gas made up of UD quarks, antiquark, equal number of antiquarks and gluons. So you can calculate the temperature at which the energy density equals to the energy density inside a proton. So what is the energy density inside a proton? How do we find out? Because the energy proton has is the rest mass energy. You know that E is mc square and rest mass and energy are same. So and then if you divide this rest mass energy by the volume of the proton, because how can you calculate the volume of the proton? Because radius of a proton is of the order of 0.85. If you consider a proton as a spherical object, so then its volume is given by 4 pi into 0.8 Fermi whole cube, and the rest mass of the proton is 0.94 GeV, 940 MeV. So if you divide ml by v, what it gives you the energy density inside the proton. So what does that mean? That means it is the energy by which your quarks and the quarks inside the proton are confined inside the proton. So what is the energy density for a Quark-Gluon gas? This I am not going to derive here. Maybe you can have some discussion in your QGP theory class, or otherwise also this is not very difficult to derive. One can show the energy density of an ideal Quark-Gluon gas in absence of any interaction can be shown as 37 pi square by 30 to the power 4. So why 37? This 37 is the effective number of degrees of freedom of a Quark-Gluon gas made up of U and D quarks. So if you then equate the two, you get what is the temperature necessary, because this is the energy density inside a Quark-Gluon gas. So if we can create a system where the energy density is of the order where the energy density is of the order is same as that inside a proton, then the up and down quark inside this proton will no longer be confined. So you can just if you equate the two, you can get a temperature T which is of the order of 130 MeV. And if you convert it into the Kelvin, so it will be 10 to the power 12 degree Kelvin. So how do you understand it physically? Because if you look at the temperature, this temperature is equivalent to the rest mass of pion, because you know the pion has a rest mass of 130 or 140 MeV. So how do I understand this picture physically? Suppose you have a pion gas, or suppose you have suppose you have a pion gas, and you start increasing its temperature. So initially, what will happen? The kinetic energy of the pions will increase. Okay, as you keep on increasing the temperature. And when you reach to a temperature T equal to 130 MeV or 140 MeV, which is the rest mass of the pion, there might be particle production from the there might be particle production because the thermal energy is enough to create many pions in the system. So many pions will start producing in the system. Now these pions have a finite size. So what will happen as a result? These pions will start overlapping with each other, because if you increase temperature, more and more pions will be produced in the system. And there are already some pions, so they will start overlapping with each other. And eventually, this is a system will come where you cannot identify a Q cube or pair corresponding to a particular pion. Instead, you have a dense multi-environment of quark, antiquarks, and gluons. So this is what is basically QGP. So this is the under critical temperature in a baryon-less medium. The critical temperature you can calculate it in this way. The critical temperature required to create a QGP is of the order of 130 MeV, which is basically equal to the rest mass of pion. You know from the all the finest lattice calculations, you all know now the temperature is the transition temperature for QGP production is of the order of 155 or 160 MeV. So which basically tells you such order of magnitude calculations doesn't give you at all any bad approximation. Similarly, you can calculate the critical net baryon density for a system at vanishing temperature. You can consider nuclear matter, okay, the normal nuclear matter. What is the density of the normal nuclear matter? You can calculate ρ0, the density of the normal nuclear matter. You can just divide the mass of the nucleus by its volume. So A is the mass number of the nucleus, because this will give you the number density. The mass number of the nucleus divided by its volume. And if you do that, you will get a value 0.16 per Fermi cube. This is the normal nuclear matter density. So what is 1 by ρ0? 1 by ρ0 is basically the volume occupied by a single nucleon, because ρ0 is the number of nucleons per unit volume. So if you take inverse of that, that will give you volume occupied by a single nucleon. And if you do a 1/3 of that, because v to the power 1/3 gives you the size. So in this case, 1 by ρ0 will give you the internucleon separation, right? So internucleon separation is 1 by ρ0 to the power 1/3. That will give you, this is the which is of the order of 2 Fermi. This is the separation between the two nucleons inside a nucleus. Okay, and that's why they do not collide with each other. Now, if the nuclear matter is compressed, that means the number of nucleons remaining the same, but if you reducing the volume available to all these nucleons, if that means you are somehow you are applying pressure and you are compressing. So the number remains the same, but the volume is decreasing. So the density is nothing but number by volume. So density will be increasing. So if the nuclear matter is compressed, what will happen? The internuclear separation will start decreasing. So and the density will start increasing. Eventually, a situation will come where nucleons will just touch with each other, because we know the nucleons have a finite size. So nucleons will just touch with each other. So the condition when the internuclear separation becomes equal to the nucleon radius, the nucleons will just be touch with the nucleons will be just touching with each other. And if you increase the density further, that means you apply more and more compression, then what will happen? The nucleons having a finite size, they will start overlapping with each other. And as a result, we cannot identify the 3 pairs of quark U and D to a particular proton, or U, D, and D to a particular neutron. You cannot do that. You cannot identify a 3 pairs of quarks, cannot assign a 3 quarks to a particular barrier. Instead, again, we have a dense multi-quark environment. And the critical density, if you do the calculation, you will find this is of the order of 3 to 4 times the normal nuclear matter density. Okay, so we just talked about, hello?
Partha?
Yes.
Hello, can you hear me? I think how many slides you have? Otherwise, I think this is the probably right place to stop today, and maybe you can continue tomorrow or whatever you like. If you have not many slides, then fine. Otherwise,
Okay, so then maybe I will start from this evolution of the heavy ion collision experiments, and then I will discuss a bit of this experiments on Glauber model. Maybe I will do it then tomorrow.
Yeah, I think that would be better. I think because we have another one more lecture.
Okay, so then just let me ask anybody if anybody has any question up to what has been taught up till now, because I have been discussing very basics today. So just I want to ask if anybody has any question till now. Does anybody have any question?
Hello, sir.
Yes, please. First tell me your name. Whoever is asking question, first tell me your name and then your question, please.
My name is Bhagirath Sahu.
Who?
Bhagirathi Sahu.
Okay.
Sir, is there any specific reason that you are choosing gold nuclei in RIG and lead nuclei in LSC?
This is a very interesting question, in fact, but probably it depends on the type of the machine, because both of them are collider machines and both of them are synchrotrons, and both of them are collider machines. So it basically the machine parameters. So one is basically the accelerator group or the machine group who tells you to the physicist that these are the nuclei which can be accelerated to this certain energy. But apart from so far as the physics is concerned, there is no particular reason why lead should be favored than gold or why gold should be favored than lead. Anybody, is it clear to you, Bhagarath?
Yes, sir.
Okay, so anybody having any more question, please ask, because I have been going very slow today. Because as on the very first it was told that our idea is not to discuss so many things, but we will discuss small things, but in a relaxed manner, so that we have a maximum transmission between you and me, between the teachers and the students. Anybody else having any question, you may please ask. Hello? Is it clear what we have discussed today? Hello? It seems no, there is no more question.
Yes, sir.
Yeah, yes, hello?
Hello, sir.
Yeah, you please first tell your name and then what do you want to ask?
Yeah, this is Priyanshi. I wanted to ask that in the beginning you were saying about entropy being high. Hello?
Yeah, please continue.
Yeah. Entropy being higher in the HRG phase and lower in the QGP phase, if I heard it right.
Did I tell that? If I told that, then it is absolutely wrong. So
Yeah, okay.
the QGP phase, very good that you have enough courage to asking this question. So entropy is more in the QGP phase and much smaller in the hadronic phase. Because all you will see eventually all these scales will be number of effective degrees of freedom. For example, for barrierless system, you will see entropy goes as GT okay, with after some constant. Apart from the constant, it goes as GTQ. And G is the number of associated degrees of freedom. So the QGP phase entropy is much more than your hadronic phase. So is your energy density, so is your pressure, all such things. Okay.
Okay.
So what discussed entropy, I think I discussed entropy in the context of first order and second order phase transition. What I said, first order phase transition, your entropy is discontinuous. Your QGP, your one phase has higher entropy and your it has nothing to do with particularly for hadron to QGP phase transition. For any kind of phase transition, if it is a first order phase transition, then there is a discontinuity in the entropy. That in the phase 1 and phase 2, the entropies are different. Okay, and this difference of entropy, if you plot the entropy as a function of temperature for a first order phase transition, you will see this discontinuity or difference of entropy happens at a constant temperature. Okay.
Yes.
T into delta, this temperature is the transition temperature, and T times this discontinuity. Delta is the difference of entropy, then T times delta give you the latent heat of transition.
Yes, yes.
At QGP, if you consider this QGP to hadron phase transition, if you can consider it in the light of a first order phase transition, in that case, of course, you do have a discontinuity in the entropy density, and you have a non-zero latent.
Okay. Okay.
And in that case, of course, always the QGP phase will always have a higher entropy compared to our entropy density, because you will see in our field we always talk about, in relativistic heavy collision we talk about energy density, entropy density instead of total entropy or total energy. Why do we do so? Any idea?
Because the volume is changing.
Very good. Very good. So first of all, the volume itself is uncertain. It is not very directly determined, and it's in an expanding system. So that is why we always talk about the when we talk about the thermodynamics, we talk about the entropy density or energy density or net barrier density. Very good.
Okay. Thank you, sir.
You are welcome. So anybody else having any question, please ask. Because tomorrow we have to go in a faster pace, because today, because of these technological difficulties, we can't cover what we are supposed to cover. So if anybody is having any question, please ask. Otherwise, I just keep on I have prepared a set of problem sheets. I have prepared a problem sheet with a very simple 10 simple problems. So I shared it with Siddharth. So Siddharth,
Yes, Partha.
will you circulate that assignment, because I want the students to work out the problems. So
Yes, I will circulate, but for that only I have one small request to all the participants who have not done the registration. Could you please write me an email? I am writing down my email here so that I can circulate to everyone, because I can get the emails of all the registered participants from the web page, but those who have not registered, could you please send me an email? I just shared my email ID. So those who have not registered. Yes, Partha, I will circulate that.
okay. Okay, so if nobody has any further questions, so I stop here, and we will start from the evolution of the relativistic heavy-ion collision experiment. We'll start from there tomorrow.
Okay, thank you very much.